Okay, let's get started. So welcome to Lab 3 demo. This lab, I think, is maybe a little friendlier than some of the other ones, but we'll see if you agree with me. And also this demonstration is probably going to be a little bit shorter than most as well, which hopefully is a positive to all of you. Okay, so let's dive into it. So in this lab, you have two main objectives. The first one is that you're going to experimentally measure and theoretically model the performance of a tankless electric water heater. All right, so that type of water heater, kind of a demonstration unit of it is shown in this picture, and that's what's on the counter in the back of the room over there. In sort of home applications, these types of heaters are what replace traditional hot water tank heating systems. So you can have kind of hot water on demand and you don't have to wait for your hot water tank to refill to get more hot water, for example. And the second, so that's our first goal of this experiment. The second goal is going to be to quantify the performance improvements due to reduced heat loss when the unit is insulated. So we're going to be doing the same experiment essentially twice, once where our system is insulated and once where it's not. So this is a little schematic of our system. So essentially we have water coming in through an inlet, and then it passes through this tube and comes out the other side. These lines right here are resistive heating elements. So essentially you can think of this as giant resistors, which of course heat up when you pass current through them. That is exposed to the water passing through the system. So that's how the water is being heated. Okay. So the main idea is cold water in, hot water out, and we're applying electrical work in order to do that heating. Okay. So in this experiment, you are going to vary the power input to two resistive heating elements. And each time that you do this, you are going to record the inlet and exit temperatures as well as the gauge pressures. Okay. Then you're going to compare your experimental water rise, which is the temperature at the exit minus the temperature at the inlet, to a theoretical rise model that we're going to derive based on conservation of energy. All right, and so our theoretical model will change based on the power input values that we're using in the experiment. All right, and then finally, we're going to look at the impact of insulating the tank by covering it with a styrofoam cover. All right, so in general, very similar to what we've done in our past experiments. So we're going to do an experiment, and we're also going to do some theoretical calculations and compare theory versus the experimental results. Okay. And then just as a reminder, I think most of you are in my class actually, but for those of you who aren't, this is very closely going to follow kind of the open system control volume analysis that we've been talking about. So yeah. Perfect timing. Okay, so let's talk a little bit about the equipment that we're going to use in this experiment. It's in the back corner of this room. Just the order from this picture is different. So the thermal management and supply unit. So what we're controlling our resistive heating unit, our resistive heating elements with, is on the right-hand side of our heater. And then the pressure gauges and stuff are on the left. Okay, so essentially how this works is we have power cables that are connecting our auto transformer output to the panel multimeter input. So that is happening here. And then the panel multimeter is connected to the resistive heating element. Again, with power cables, these are the curly ones right here. So the cables that are going from that unit to the heater are those ones. They're black and red on the base of the heater. All right. Our auto transformer with a rheostat looks like this. You can see them on the front of this picture here. So these guys right here is just this. All right. And then we're also going to make use of a watt meter, which is below. So that is this guy right here. The power uncertainty is plus or minus 0.3% of whatever your power reading is. So keep that in mind. And then also, this is a very important note. Make sure that you keep the current below 10 amps for this experiment. This is a safety requirement, so just be careful with that. I mentioned that we have to measure temperature, so we're going to do that using thermocouples. Which are sensors that measure temperature, of course, and they have an uncertainty of plus or minus a half a degree Celsius. Keep in mind that it's going to read out the temperature in a different unit, so just be careful with that. So it's going to give you the temperature in Fahrenheit. And then you can turn the knob on that readout to switch between the channels, so that will give you different temperature readouts on the system, okay? We are also going to be measuring volume flow rate. And we're going to use a mass flow, a volume flow rate meter, just like how we did in experiment 1. So the vertical one that has this little floating disc in it is the same sort of volume flow rate meter that we're going to use in this lab. And so just make sure that you measure the volume flow rate by reading the location of the max diameter of the float. So that is right here. Okay. The uncertainty for this is, again, plus or minus 2% of the max volume flow rate. All right, so this is the same as in lab 1. So when you're in the lab, just make a note of what the max tick mark is on that scale, and then your uncertainty is going to be plus or minus 2% of whatever that value is, okay? Okay, so for data collection, what you're going to do in the lab is you're going to collect data for 10 to 12 different power readings with approximately equal increments of increasing power. So just make note, this is not increasing voltage, we're increasing power. All right, the first reading should be taken at the lowest power, and the last reading should be taken at the highest power setting, which is about 1 kilowatt. The reason for that is strategic. So since we're heating water in this unit, we want to start with the lowest temperature heating, right? So that we don't have to make it or wait for it to cool down before we do the next run. So if we had started from hot and worked our way down to cold, it would just take a whole lot longer to do the experiment. Okay, so when you're taking data in the lab, you're going to want to fill out a table that looks like this. Obviously, I don't have enough rows included for you here, but this is the general format of the data that you want to collect. So for each one, each experiment, you're going to record the power input in watts, the gauge pressure at the inlet and the exit, the temperature at the inlet and the exit, and then you'll use these two columns to calculate here. So we have TE minus TI, and then the theoretical temperature rise and the uncertainty of the theoretical temperature rise, you're going to use our theory calculations that we're going to talk about in just a second, but you'll put experimental values into that equation to get those values. So you'll use experimental data in the theoretical equation. These. All right, and then the uncertainty of the theoretical temperature rise, just like all the other labs, we're going to end up with a theoretical equation for temperature rise. And so we're going to need to calculate uncertainty. So U of TE minus TI using the equation from lab 0. Which hopefully everybody feels very used to by now. Okay. One small note here, do not panic if you are getting pressure values that are quite low. So we're using fairly low flow rates here. So that's to be expected. So don't worry. Okay. So you're going to tabulate all of this data, essentially monitoring what's happening at the inlet and the exit as you vary the power input. You are also going to do some surface temperature measurements, but only for 2 cases in the above table. All right. So when you're at steady state for the lowest and the highest power settings only, so don't do this for every single one of the entries on this table up here, just do it for the first and the last one. You are going to measure and tabulate the surface temperature of the heater with an infrared thermometer. All right, so it's this guy right here. I suspect you guys have all probably used something like this before, whether to measure like your own temperature. So these are like the forehead scanning temperature type things. Works just the same as like a police radar gun. So it's just a point and shoot sort of a thing. So what you do is there are going to be 11 temperature target points that are marked on the water heater itself. So for each of those points, you're going to point the thermometer at that point, hold the trigger until the temperature displays. Pretty easy. Okay. The uncertainty of this instrument is plus or minus 2 degrees C, and the target points are spaced 1 inch apart. We measured that for you, and we're going to let you assume that there's no uncertainty in that measurement. Okay. So no uncertainty. I mean, of course there is, but just ignore it. Okay. Okay. So, you've done this twice, right? And so now you're going to do essentially, you're going to go back to the start of your data collection and you're going to do all this stuff again, but with the insulating cover on top. Okay. So you will go through and do 10 to 12 different power inputs, measure the pressure and the temperature at the inlet and exit. And then you're also going to do these temperature, surface temperature measurements for the lowest and the highest case. Okay. All right. After you are done with your experiment, this is very, very, very important. Just like not exceeding, what did I say it was, 10 amps? So just like not exceeding the 10 amps, also be very careful that when you're finished, you turn off electrical power before you turn off the water flow. All right, so if you do this in the reverse order, you'll hurt the apparatus, and that would be very sad. So please don't do that. Okay. If something does happen like this, let us know immediately, though. Okay. That would be much preferred to subsequent groups realizing that they got trash data. Okay. All right. Okay, so I mentioned that we are going to use a theoretical model. So that's what we're going to work through now. So the first thing that I'm going to do is I'm just going to sketch out our system again. So this is going to be essentially a recreation of that little schematic on the first page. So we have an inlet and an outlet. All right, so we've got our cold water inlet and then a hot water outlet. And at each of those locations, we have a mass flow rate, a temperature, and a pressure. And this is gauge pressure. So everything at the inlet, I'm going to give a subscript I. And then I have all of these things as well at the exit. So I'm going to note these with an E. So again, this is gauge pressure. Okay. We also have our heating elements in here. All right. And when we theoretically analyze a system like this, the first thing that we want to do is we're going to draw our control volume. All right, it's a control volume because mass is flowing in and out, right? Otherwise it'd be a system. So I'm going to draw my control volume just as essentially the heater system itself. All right. The next thing that I'm going to do is I'm going to write down our governing equations. It's good practice to always start with the full equation, even if you know it's going to be something simpler, just to make sure you don't accidentally get rid of terms that you might need. Okay, so the first one that we have is conservation of mass. And then we will also have conservation of energy. All right, so conservation of mass is just the time rate of change of the mass in our control volume. And that is equal to the sum of the mass flow rates in minus the sum of the mass flow rates exiting. Okay, and then we also have conservation of energy, which looks similar, but has a bunch more terms. So we have the time rate of change of the total energy inside the control volume is equal to the heat transfer leaving the control volume minus the work done on the control volume plus, move this just a tiny bit. Plus we have the flow of energy coming into the control volume at each of the inlets. So this involves enthalpy, kinetic energy, and potential energy. And then we have that same term, but we need to take into account all the energy that is leaving our control volume. So I have m dot E times HE plus 1/2 VE squared plus GZ E. Okay. So far, so good. Okay. Next, we're going to list out our assumptions. So these are things that we will assume in order to simplify our two governing equations. Does anybody have any assumptions that they know we can make? No ideas? Is it too early, guys? Okay, so we can assume this is steady flow. We're waiting until our system gets to steady state, so we can assume steady. This means that we can get rid of the time derivatives, right? So I can get rid of the left-hand side of both of these equations. I'm also going to make the assumption that the change in potential energy is 0. All right, so our elevation change for this system is really not impressive. It's nothing at all. So I can get rid of these two terms here. This isn't really an assumption, but more just a comment. We only have one inlet outlet. So our sum over the inlets and sum over the outlets is just a sum over 1. So we can just kind of get rid of these summation signs, right? And I'm also going to neglect heat transfer. So we're going to assume an idealized system. Which means that Q dot CV, we're going to be setting to 0. We obviously cannot get rid of work because we're putting electrical work into this and we're measuring the power that we're inputting to it. So that term's important. Enthalpy is also generally important. So if you're in my class, we've talked about how large the enthalpy terms are for systems like this. So we definitely need to keep those. But we also compared the kinetic energy terms to enthalpy, and we saw that they're usually very, very small. So for that reason, we're going to neglect the kinetic energy. Red. All right, so I will get rid of these. All right, so now we are going to write our simplified equations. So for mass, all I have is that 0 is equal to m dot I minus m dot E, which means that m dot I is equal to m dot E, and I'm just going to call that mass flow rate m dot. Okay. Keep in mind that we are measuring volume flow rate. So since we're measuring V dot, then we'll need to make use of m dot is equal to V dot over the specific volume. All right, so that'll be a handy little thing to remember when you're putting in your experimental data, okay? And then for conservation of energy, we have 0 is equal to minus W dot of the CV plus M dot HI minus HE. Okay. Remember that W dot CV is equal to W dot out minus W dot in, right? We're not getting any work output from this system, but we do have work going in. So that means that our equation turns into 0 equals W dot in, because we have a negative times a negative, plus M dot HI minus HE. Okay. Okay, so we're getting pretty close. If you remember when we started this whole thing, we wanted to find a theoretical temperature difference, right? So I don't see any temperature differences in these equations yet. So what we're going to use is we are going to assume that water is incompressible and has a constant specific heat. Oops. C. Then we can write that HI minus HE is equal to C times the temperature difference plus the specific volume times P at the inlet minus P at the exit. Okay, so I am just going to substitute this expression in here, which gives us that 0 is equal to W dot in plus M dot times the quantity of everything that's in the orange right here. So we have C times our temperature difference plus specific volume times our pressure difference. Okay. So we're just going to solve this for Ti minus Te, and that will give us our theoretical value of the temperature difference. And we get 1 over C times the quantity of W dot in over M dot minus specific volume times the pressure difference. All right. Okay. I'd like to point out a few things in here. So the specific heat and the specific volume, these are things that you will look up in tables. Right? W dot, M dot, PI, and PE, these are all measured quantities. Okay? So when you're doing your uncertainty analysis for this theoretical temperature difference, you're going to need to account for the things that we have measured, of course. So you're going to need to account for uncertainty in the power input, volume flow rate, and pressure. And you can neglect uncertainty for the things that you get from a table. So C and D. Okay, does that make sense? And then this, of course, is the equation that you're going to use to do your analysis of uncertainty to find the uncertainty. Okay. Okay. Experimental temperature rise in uncertainty should be 2 times the temperature uncertainty. So when you're doing delta Ti minus Te experimental, this is going to be 2 times delta Ti, for example. Okay. Any questions so far? Okay. So the last thing that I am going to tell you about is the plots that you'll need to make for this lab. I apologize. These example figures, I think that the font could be a bit bigger on these for my taste. I think they're a little hard to read. So just bear with me here. So the first plot that you're going to need to create in this lab report is the temperature rise. So we want to look at temperature rise, so Te minus Ti in degrees C versus electrical power input. And you are going to have 2 sets of data that will be displayed as markers because these are experimentally measured. So you're going to have your set of data for the non-insulated case, and then you're going to have a set of data for the insulated case. All right. In addition, you are going to also calculate the theoretical temperature rise, and you're going to plot this as a line. All right. So if you remember back to this equation here, this is your horizontal axis, right? So this is your power input. So you can just put in any number that you want for the power input and predict the theoretical temperature difference, right? So that is going to be displayed as a line. And then you have uncertainty for your prediction of the temperature rise. So instead of putting error bars on a line, because that would be quite strange, we are going to use what is called an error band. So if you imagine that you have this point on your theoretical prediction, you have uncertainty for that, of course, which would look like this. But since we're not displaying this theoretical prediction as individual points, but we're using it as a line, we are going to use error bands, which essentially are just the lines that show you the top and the bottom parts of the error bars. Does that make sense? If you want to see how to do that in MATLAB, I've put that in my MATLAB example video that's on Moodle. And the same procedure can be used in Excel too. Okay. Any questions on this plot before I tell you about the next plot? No. Okay. The next plot is going to be the surface temperature plot. So if you remember, we were doing temperature measurements over the surface of our heater for the min and max power inputs. And then we're doing that for the insulated case and the non-insulated case. So you'll have 4 sets of data that you're going to plot. You're going to have non-insulated lowest power setting, non-insulated highest power setting, insulated lowest power setting, and then insulated highest power setting. All right, so you'll get 4 sets of data here. And then you'll notice on this example plot, I only have error bars on the vertical direction for temperature because we're ignoring the uncertainty for the placement on the x-axis, okay? Any questions on this plot? No? Okay. All right, so last but not least, in your report, make sure that you, in your discussion, answer the following questions. So we would like you to think about how well the experimental data insulated and unsulated and the theoretical model compare with each other. All right, how much improvement, if any, did the insulation offer in correlating to the theoretical model? And then what possible reasons are there for any discrepancies between the 2 sets of experimental data to the theoretical model? Did the insulated water heater align perfectly with the theoretical model? If not, why? And when you're answering that question, consider the assumptions that we made to derive that theoretical model. And then last but not least, some households opt for this type of on-demand water heater, like I mentioned at the beginning of this, to supply their hot water needs. So this is instead of a hot water tank. So we would like you to conduct some online research and then comment on the advantages and disadvantages in terms of economics and performance for this type of on-demand water heater. And then as with any sort of research that you do for lab reports, make sure you cite your references and comment on their validity. And that is it.